Hi, in this presentation, I'm going to explain Leibniz rule, which is a formula for taking higher derivative of a product of two functions, but more importantly, I will focus on what makes a proof trustworthy, not just what this result is true. So, before going, I wanted to explain why Leibniz rule matters. In many real-world situations, especially in physics, we deal with functions that are multiplied together, like a polynomial times an exponential. When we take higher derivative of these, it becomes very repetitive and time-consuming if we keep applying the product rule again and again. Right, Leibniz rule gives us a more efficient way to do this by providing a general formula for any number of derivatives. So we start with the basic product rule, which says that the derivative of a product is f prime multiplied by g plus f times g prime. This works well for the first derivative, but once we go to the second or third derivative, the number of terms increases quickly and the expression becomes more complicated. If we compute a few derivatives, we start to notice a pattern. The number of terms keep increasing, and the coefficients begin to follow a structure that looks like binomial coefficients. This suggests that there might be a general formula that works for any number of derivatives. So if you guys look, you can see that the first derivative looks like 1, 1, second one looks like 1, 2, 1, third one looks like 1, 3, 3, 1, which is the pattern of binomial coefficients. So Leibniz rule gives us that general formula. It tells us how to compute the nth derivative of n of a product using a sum, where each term involves the derivative of f and g, and the coefficients come from binomial coefficients. This allows us to avoid repeating the product rule over and over again. So why rigor is needed? At this point, it might feel like we just trust a pattern, but this is where rigor becomes important. Just because some things work for the first few cases does not mean it always be true. In mathematics, we need a proof that shows that the formula works with all values of n, not just small examples. So the proof structure to make it the result trustworthy, we use mathematical induction. And as we know that to prove it by induction, we first have to use the base case for n equal 1. Then we have to assume that the formula holds true for some n. And then we have to prove that the formula holds also true for n plus 1. These steps use the product rule and algebra to show that the pattern continues, and this is what guarantees that the formula works for all natural numbers. So the base case is very easy. We know that it's always true for n equal 1. Now, for the inductive step, quick details about it is that now we're going to differentiate both sides of the assumed formula. We use linearity of differentiation to bring the derivative inside the sum, which allows us to work term by term. Next, we're going to apply the rule to each term. This splits each term into two parts, one involving the derivative of f and one involving the derivative of g. And this is where the expression naturally separates in two sums. Then we arrange the sums so they can line up properly, and we index one of them and combine them. After that, we have to use the Pascal identity to combine the coefficients into a single binomial coefficient, and this gives us a formula for n plus 1. And just so after simplifying everything, we get exactly the same structure again, but for n plus 1, and this completes the inductive step and finishes the proof. So where intuition can fail. So after going through the proof, it becomes clear where intuition can fail. At first, the pattern looks obvious and it's tempting to accept it right away, but the proof shows that there are important steps like combining terms and reindexing sums. They're not obvious without careful reasoning. And if we skip justifications, the result might look correct, but not actually be fully reliable. So intuition helps us to see the idea, but rigor is what makes it trustworthy. I also, when I asked ChatGPT, his stances was that it was correct and well structured, so it looks very convincing. However, it has some limitation. It uses vague assumptions and moves quickly through steps without fully explaining them, and because of this, it can be harder for a beginner to fully understand. So even though it looks reliable, it still needs to be checked carefully. And it could be hard for beginners to understand it without actually explaining. So why does this matter beyond math? Honestly, this idea shows up outside of math more than we think. For example, with AI tools like ChatGPT that I use for this project, answers often look very clean and convincing, but that does not always mean that they are fully reliable. You still have to check the reasoning. The same is true for science and even everyday decisions. Just because something sounds right or looks professional does not mean it actually is correct. That is why learning how to verify things step by step is important, not just in math, but in general. So to conclude, Leibniz rule gives us a powerful way to compute higher order derivatives of products in a structured and efficient way. But more importantly, this project shows that the value of a formula is not just the result it produces, but in how we know that it is true. A proof is trustworthy when every step is clearly justified, when assumptions are precise, and when we can follow the reasoning without gaps. Without that, even a correct result can feel uncertain. So overall, this helped me understand that in math, trust comes from verification, not acceptance. And yeah, thank you guys.